All right, we are going to dive more into Unit 13, talking about rates and in a later video, equilibrium. So what is a chemical reaction? So a chemical reaction is a process that involves the rearrangement of atoms, but you knew that already. You also already knew that the law of conservation of mass states that mass is neither created or destroyed. So we balance chemical reactions to illustrate the law of conservation of mass. So I want you to take a second and I want you to balance and model the following chemical reaction. If you balanced it correctly, you should have put a 2 in front of the hydrogen and a 2 in front of the water to have it nicely balanced up. So how are the atoms being rearranged here? So in our reactants, our hydrogen and our oxygen are separate from each other. And for every 2 hydrogens we have, 1 oxygen breaks off and bonds with them to create that water molecule, leaving that leftover oxygen to go bond with another hydrogen. So we need twice as many hydrogens as we do oxygens in order to create our amount of water. So like you see in this reaction, sometimes you have a double arrow. And there are double arrows in reactions when those reactions are reversible. It means that they can go one direction, but they can also go in the opposite direction. So while we're used to reading chemical reactions this way, since it has the double arrow, water can also be broken down into oxygen and hydrogen as a chemical reaction. So like I was saying, reactions can be reversible, meaning that the products can rearrange to form the reactants. So how chemical reactions occur? So you remember back from first semester when we talked about collision theory, which states that molecules must collide with enough energy and in proper orientation in order to react. So do all reactions require energy to occur? Yes, energy is required for molecules to collide. One of those things is called the activation energy, and this is the minimum energy required for a chemical reaction to occur. A high activation energy slows down the rate of reaction because it takes a while to get enough energy to overcome the activation energy. Meanwhile, a low activation energy speeds up the rate of reaction because it requires less energy in order for the reaction to happen. So what do we call a reaction that absorbs energy? We call that endothermic. And what do we call a reaction that releases energy? We call that exothermic. Review from our last video. And here's a nice little picture of collision theory for you. So energy in reactions. Once the reactants have gained enough energy, that activation energy, they are considered to be the activated complex. So in other words, the activated complex is the reactants, but they have a lot of energy in them now. After the activated complex state, the reactants will rearrange to form the products. And this is where a new word for you comes in called enthalpy. And enthalpy is the change in energy in a reaction. So the change of energy from what we had at the beginning to what we had at the end. And it is represented by something called delta, that little triangle sign, H. Endothermic reactions are going to have a positive delta H, and they will feel cold to the touch. And exothermic reactions have a negative delta H, and they feel warm to the touch. So here are some reaction diagrams for what we've been talking about. You can see our activated complex up here at the top of both reactions. And you can see that our delta H is the difference between the energy of the reactants and the energy of the products in both cases. Over here we have our endothermic reaction, and you can see that our delta H is positive when we've gained energy as we've gone along. And over here is exothermic, and energy is released because we have less energy at the end than we started with, meaning we'd have a negative delta H. So this brings us to catalysts and inhibitors. So you already learned about catalysts, and they're a substance that speeds up a reaction without being consumed. So they're not part of the reaction. We don't see them on the reactant side or the product side. So how do catalysts work? They lower the activation energy, so now it takes less energy for that reaction to take place, meaning it's going to go faster. So they increase that rate of the forward and the reverse reaction though. So if it's one of those double arrow reactions, it's going to make it go faster in both directions. The example of a catalyst that you learned about back in biology is an enzyme. And you'll remember enzymes are a large molecule, usually a protein, which catalyze biological reactions in your body. Now, something you may not have learned about before is an inhibitor, and this is a substance that actually slows down a reaction without being consumed. So it, in some ways, is the opposite of a catalyst. They're the same in that they are both neither reactants or products of a reaction, but an inhibitor slows things down. So they decrease the rate of the forward and the reverse reaction. So we can see in this diagram here, we have in blue our original chemical reaction with our delta H. Now you'll notice the delta H stays the same with the catalyst, but the activation energy is the only thing that is lowered, allowing this reaction to happen quicker. So let's talk some more about enthalpy. So enthalpy is the amount of energy transferred between the system, which is the reaction, and the surroundings, where the reaction is happening in. So delta H actually equals the product minus the reactants, just like delta T did. Remember, if you get a positive delta H, you have an endothermic reaction. So that means more heat goes from the surroundings into the system. So you take heat that's in the air and from the light, and you're putting it into the chemical reaction. And if you have a negative delta H, it is an exothermic reaction, and heat is actually leaving that chemical reaction, which is why it feels warm to the touch, and going to those surroundings. Remember, energy is not created or destroyed, it's just transferred between the system and the surroundings through the law of conservation of energy. So let's look at the burning of a match. So we have our system, which is going to be our matches, our reactants, and then we have these surroundings, everything all around it. So we need a certain amount of energy to start the reaction, and the striking of the match is going to be that activated energy. After our match has burned and the reaction is over, we have a difference in the energy we started with and the energy we finished with. And since energy was released as heat, you know matches feel warm, we know it is an exothermic reaction. So this brings us to Hess's law. So Hess's law states that the enthalpy of a whole reaction is equivalent to the sum of its steps. So all reactions have a delta H. Anyone out there, you can usually look up a delta H value for it. So most substances have a known delta H, like I was saying. The delta H is usually measured in units of kilojoules, lowercase k, uppercase J. And the change in enthalpy is caused by bonds breaking and bonds forming. So let's look at an example together. The formula 2H2 plus O2 produces 2H2O, that equation we balanced at the beginning of the video, has a known delta H value of negative 967.2 kilojoules. What about the reverse reaction? We said that that reaction was reversible. So if we put everything in reverse order, so we start with the water instead of finish with, you'll notice that we have the same delta H value, it has just become positive. So when you take a reaction and you reverse it, you just switch the sign of the delta H. Additionally, we can change the superscripts, the coefficients, the things in the front. So what if we tripled the amount of water? So we multiplied everything by 3. So if we multiplied everything by 3, we would also multiply our delta H by 3. So if we had 6 waters and 6 hydrogens and 3 oxygens, we would have 3 times 967.2, which if you enter into your calculator, you will see is 2,901.6. So anything you do to an equation has an effect on the delta H, but it is a predictable effect. If you reverse it, you change the sign. If you multiply through by something, you have to multiply your delta H by that same amount. So Hess's law allows us to add chemical equations to determine the potential delta H for a reaction that we don't know the delta H for. So we can add reactants and products and delta H's together. We can also simplify, meaning get rid of things that appear on both sides of the equation. We can multiply by coefficients like we did in that last example on the previous slide, and we can reverse the reaction like we did on the previous slide. So if a reaction is reversed, remember the delta H is also reversed. So if we have our 2CH4 plus O2 producing 2CH3OH with a delta H of negative 328, if we reverse our reaction, it becomes positive, just like you saw before. And remember, if the coefficients of a reaction are multiplied by an integer, the delta H is also multiplied by that same integer. So if we have this chemical reaction and we multiply everything by 2, we have to multiply our delta H by 2. So some tips for this. You want to look at the final equation that you were trying to create first. Your Hess's law problems are always going to say, this is our chemical reaction we're trying to create. You want to look at that first. And you're going to find a molecule from that equation that is given in only one of those given equations. So you're going to be given a bunch of other equations to use. You want to find a molecule that is present in only one of them. Look at each reaction and determine if the products and the reactants are on the correct side of the equation. If not, remember you can flip-flop the reaction around. Look to see if the reaction will provide the correct number of reactants and products. If not, you're going to multiply through by a coefficient. And next, you're going to alter remaining equations to get things to cancel that do not appear in our final equation. So let's do some examples together so you can see what I'm talking about. So example number 1. When methane is burned in oxygen, carbon dioxide and water are produced. So we have methane plus 2O2 produces carbon dioxide and 2H2O. And we are asked to calculate the change in enthalpy when methane is burned using these 3 reactions here. So this is the reaction that we want to get, and we need to use these 3 reactions to make it happen. So let's take a look. We can see in equation number 1 that the CH4 is on the wrong side for what we need it to be on. In our original equation, CH4 is on our reactant side, the left side. But in this equation, it is on the right side, the product side. So we're going to need to reverse that equation, put the CH4 in front and the C plus 2H2 in the back. But that also means we'll change the sign of this delta H from a negative to a positive, like that. So that brings us to equation 2, where everything appears to be on the correct side and everything is in the right amount, so we can just leave equation 2 alone. For equation 3, we quickly see that we need to have 2H2O and we only have 1 H2O over here. So we have to multiply the whole thing through by 2. Can't just do the water, we have to do the whole thing. And that also means we have to multiply this delta H by 2. So right now, this is what we've done. on our previous slides. So we write that all out as one long equation, and you cross out anything that appears on both sides of the arrow. So we had a single carbon on both sides of the arrow, it gets canceled out. We had two H2s on either side of the equation, it gets canceled out. Now you'll notice we had two O2s left over on the reactant side. So after we canceled everything out, we want to add those together to get CH4 plus 2O2 produces CO2 plus 2H2O. Now that we know that we have everything correct, we add our three numbers together. Remember, if it's a negative sign, it's technically subtracting. And we get the answer of negative 890.36 kilojoules. I like to think about Hess's law problems like they are puzzles. I don't think they are actually that hard. They just require you to use your brain and think it through. They're kind of like balancing chemical equations. You might take a little bit of trial and error, but you'll get the hang of it. So let's look at another example. So we are told that methanol-powered cars are an idea for alternative fuel. What is the change in enthalpy for a reaction of methanol burning in a car? And then we're given this chemical reaction and asked to solve for what the delta H is. We are then given two additional equations that you can see below and their delta H. So let's see what we're going to do with those. Once again, we have our original equation, and we have the two equations that we were given. So we look around, and one of the first things we notice is that our CH3OH is on the wrong side of the equation. It's on our products over here, but we want it on our reactants. So we're going to flip that one around, and in the process of flipping it around, we flip the sign around with it, so a negative becomes a positive. Then we look at our other problem. And we will notice that it's not quite right as far as the number of things we need. For example, it only had 2 H2O, and we needed 4 H2O. So we multiply the whole thing through by 2, which means we have to also multiply our final number by 2 to get a new number. So we bring everything down that we have written out. We cancel the things that appear on both sides. And we'll notice that we had 1 oxygen over here and 4 over there, so one of them cancels out, but not all of them, which makes that oxygen a 3. So we get our final equation that we were looking for. They should match. And then we just added those two things together for a total of negative 1,277. There's also another way to calculate Hess's law problems. And that's the sum. That's what that weird kind of E looking thing is. That's a sigma, and it means sum. So we can take the sigma of our delta H of our products and subtract the sigma, the total of the delta H of our reactants. So what does this mean? Remember, delta H is the sum of the enthalpy of the formation of products minus the sum of the enthalpy of formation of the reactants. And you look at the coefficients in your chemical equation, you must account for all the substances. And you're going to use the coefficients to multiply. Be careful adding and subtracting negative numbers to each other. This is where brackets can be very helpful in your calculator. So let's look at another example. So when methane is burned in oxygen, carbon dioxide and water are produced. So our equation, CH4 plus 2O2 produces CO2 plus 2H2O. And you are asked to calculate the change in enthalpy when methane is burned using the following. So we're given a delta H of all of those different parts. So let's take a look at how we're going to do this. So this is our formula. I've put some colors in there to kind of help you see what I'm talking about. This is the table you were given on the previous slide. So the formula that we know is delta H equals products minus reactants. So let's write that out. So we have delta H equals our products, CO2 plus 2H2O, minus our reactants. And you'll notice I put those in parentheses to help myself out later. So you're going to want to distribute that negative, which is why I put the parentheses in there. So that means it means minus CH4 minus 2O2. Now we're going to plug in our values from the chart. So these are our numbers straight off the chart. You will notice I multiply by any of my coefficients in there. So if I had 2H2O, I have to multiply the number for H2O by 2. And once you've done all of your math correctly, you should get a delta H of negative 890.36. Not so bad, right? Then let's look at another example. So using the standard enthalpies of formation table, determine the change in enthalpy for the following. We have sodium hydroxide plus hydrochloric acid producing sodium chloride and water. And then we're given our table of delta H's. So we do our setup where we take our products and subtract the reactants, making sure to distribute that negative sign. We take our numbers straight from the table. We didn't have any coefficients in this one, so that worked out great. And once we enter it all into our calculator, we get negative 177.83. So some problem solving strategies for you, because I know these problems are like puzzles, and like a puzzle, you need a problem solving strategy. So sometimes you're going to want to work backward from the required reaction, using the reactants and products to decide how to manipulate the other given reactions at your disposal. You're going to reverse any reactions as needed to give the required reactants and products. Multiply reactions to give the correct numbers of reactants and products. And most importantly, always make sure that you are using the correct sign for things. All right, that's all I got for this video. Come to class ready to solve some Hess's Law problems.